Section 6.1 Applications of Integration. Two topics. Topic 1 Velocity and net change. Topic 2 Other applications. Topic 1 Here are some basic concepts and formulas about a moving object. Consider an object moving along a line. Say, a car is traveling along a straight road. A. The position of the object is the location of the object relative to the origin. The position is usually denoted by S. Because the object is moving, its position depends on the time t. So position is a function of the time t. The position of a moving object can be positive, can be negative. For example, in this diagram, if we consider the east is the positive moving direction, and the west is the negative moving direction. Then, when the object is to the right of the origin, its position is positive. When the object is to the left of the origin, its position is negative. B. The velocity of the object is the rate of change of the position of the object. That is, velocity is the derivative of the position. This is the formula to compute velocity. Take derivative on position with respect to the time t. Then we get velocity. C. The displacement of the object over a time interval from A to B is defined to be the position of the object at the time B minus the position of the object at the time A. For example, in this diagram, I suppose when time is A, the object is here. And I suppose in this time interval, the object first move in the positive direction, then move in the negative direction. And when time is B, the position of the object is here. So the displacement is the position of this point minus the position of this point. Because this point is to the left of this point. So the displacement in this example, displacement is negative. The formula to compute the displacement is this formula. Take integral on velocity from A to B, then we get displacement. It is because velocity is derivative of position. So integral on velocity is equal to the integral on the derivative of position. By fundamental theorem of calculus, to compute this integral, we need to find one antiderivative. It is clear that antiderivative of this function is the position function. Take derivative on this function, then we get this. So by fundamental theorem, this integral is equal to plug in B, the upper limit, in the position function, minus plug in A in the position function. So we get S of B minus S of A. This is displacement. So displacement is equal to integral on velocity from A to B. One way to understand this formula is from the fundamental theorem of calculus. A second way to understand the formula is from the definition of an integral. In this integral, dt is the length of a short time period. Velocity times dt. Velocity times dt is the displacement of the object in that short time period. The displacement can be positive, can be negative, depending on the sign of the velocity. That is, depending on the moving direction of the object in that short time period. Now, sum up all the displacements from A to B. Some displacements are positive, some are negative. So when we sum up all the displacements, cancellations occur. Because of the cancellations, the result of this sum is just this. This is the displacement of the object on the time interval from A to B. We can also understand this formula geometrically. Draw the graph of the velocity function from A to B. Suppose this curve is the graph of the velocity function. Then this integral is the net area of this shaded region. The formula says that the displacement of the object from A to B over the time interval A to B is the net area of this shaded region. D. The distance traveled by the object over a time interval from A to B is the total distance traveled by the object on the interval. For example, over this time interval, a car moves first in the positive direction, then in the negative direction, then in the positive direction again. The distance traveled by this car over this time interval is this distance plus this distance and plus this distance. Distance is non-negative. On the other hand, the displacement of this car over the time interval is the position of this point, the point corresponding to the time B, minus the position of this point, the point corresponding to the time A. Because this point is to the right, to the left of this point, the displacement of this car over this time interval is negative. The formula to compute the distance traveled by the object on the time interval from A to B is this formula. The distance is equal to the integral on the absolute value of velocity from A to B. Absolute value of velocity is called the speed of the object. Velocity can be positive, can be negative. Speed is always non-negative. In this integral, dt is the length of a short time period. Speed times dt. Speed times dt is the distance traveled by the object in that short time period. Sum up all these small distances from A to B. Then the result is the total distance traveled by the object over this time interval. If we plot the graph of the velocity function on this interval, for example, suppose this curve is the graph of the velocity function on the interval from A to B. Then this integral is the total area of this shaded region. That is, this integral is the area above x-axis plus the area below x-axis. This formula says that the distance traveled by the object over this time interval is the total area of this shaded region. Now, I present some examples. Example 1. Let V, the velocity of some moving object, be given by this polynomial, where t is time. Part A. Graph the velocity function over this time interval. Then determine when the motion is in the positive direction and when it is in the negative direction. I plot the graph of the velocity function here, this curve. You can use a graphing calculator to plot the graph. From this diagram, we can see that when time is between 0 and 1, velocity is positive. And when time is between 1 and 5, velocity is negative. Therefore, the answer to part A is the motion is in the positive direction on the time interval from 0 to 1 and in the negative direction on the time interval from 1 to 5. Part B. Find the displacement over the time interval from 0 to 5. The displacement over this time interval is the position of the object at the instant 5 minus the position of the object at the instant 0. By formula, the displacement is equal to the integral on the velocity function from 0 to 5. In this example, velocity is this polynomial. To compute this integral, we need to find an antiderivative of this polynomial. It is easy to see that antiderivative is this polynomial. Now, plug in the upper limit 5 in the t. Then we get this number. Minus, plug in the lower limit in the t. Then we get this number. This number minus this number is negative 31.25. Part C. Find the distance traveled over the time interval from 0 to 5. By formula, the distance traveled over this time interval is given by this integral. The integral on the absolute value of the velocity function from 0 to 5. To compute this integral, I need to remove the absolute value. To the end, I split this integral into the integral from 0 to 1 plus the integral from 1 to 5. From the graph of the velocity function, when time is between 0 and 1, velocity is positive. So in this integral, we can directly remove the absolute value to get this integral. About this integral, time is between 1 and 5. When time is between 1 and 5, velocity is negative. So when we remove this absolute value, we need to add a minus sign here. Velocity is negative. Negative times negative, it is positive. Now move this negative sign outside this integral. Then we have this equation. Plug in the polynomial in V, polynomial in V. Then we have this equation. Antiderivative of this polynomial is this polynomial. So this integral is this number by the fundamental theorem of calculus. And this integral is this number. By calculator, this number minus this number is 32.75. So the total distance traveled by the object over this time interval is this. Example 2. Find the position and velocity of an object moving along a straight line with the given acceleration, initial velocity, and initial position. We are given this information and we want to recover the position function and the velocity function of the moving object. I have two solutions to solve the problem. In solution 1, I use the antiderivative method to recover the position function and the velocity function of the moving object. Since acceleration is the derivative of velocity, velocity is antiderivative of acceleration. In this example, acceleration is negative 32. Antiderivative is negative 32 times t plus an arbitrary constant c. Don't miss the arbitrary constant c. To determine c, I use the given initial condition. When time is 0, v is 70. So c should be 70. Therefore, the velocity of the moving object is negative 32 times t plus 70. Moreover, the derivative of the position is velocity. Therefore, position is antiderivative of velocity. Plug in this polynomial in V, then we have this equation. Antiderivative of this polynomial is this polynomial. Don't forget to add an arbitrary constant. This time I use d because I have used c here. To determine d, I use this initial condition. When time is 0, the position is 10. By this condition, then d is 10. Therefore, the position function of the moving object is this. the second solution. In this solution, I use the fundamental theorem of calculus to solve the problem. Since derivative of v is a, I take integral from 0 to t on the both sides of this equation. Then I have this equation. By the fundamental theorem, this integral is equal to this. A is negative 32. Antiderivative of negative 32 is negative 32 times tau. Plug in the upper limit and the lower limit in tau. Then this is negative 32 times t. Now move this number to the right side. Then we have this equation. By the initial condition, v of 0 is 70. Therefore, the velocity function is equal to negative 32 times t plus 70. To find the position function, I start with this equation. Derivative of position is velocity. Take integral from 0 to t on the both sides of this equation. Then I have this equation. By fundamental theorem, this integral is equal to this. Plug in this result in v, then I have this equation. Antiderivative of this polynomial is this polynomial. Plug in the upper limit, lower limit in the variable tau. Then I get the answer to this integral. Now move this number s of 0 to the right side. Then I have this equation. By the given initial conditions, s of 0 is 10. Therefore, the position function of the moving object is this polynomial. Example 3. Phil and Sasha start at the same place on a straight road, riding bikes with the following velocities. The velocities are measured in miles per hour. The time t is measured in hours. Part A, graph the velocity functions for both riders. Phil's velocity is a constant, so the graph is a horizontal line. Between 0 and 1, Sasha's velocity is 15 times t. The graph is a straight line through the origin, and the slope is 15. After 1 hour, Sasha's velocity is a constant, so when t is greater than 1, the graph is a horizontal line. Part B. If the riders ride for 2 hours, who rides farther? Interpret your answer geometrically using the graphs of Part A. In Part B, we need to determine the positions of the riders when time is 2. To answer the question, I use the displacement formula. Position at time B minus position at time A is the integral on the velocity from A to B. In this formula, I replace the dummy variable t by the variable tau. Then set A to 0 and B to t and move this number to the right side. Then the position at time t is this integral plus this number. When time is 0, field's position is 0. So field's position at time t is given by this integral. Similarly, Sasha's position at time t is this integral. Now, in this equation, set t to 2. Then, after 2 hours, the position of field is given by this integral. This integral is the net area of the region between the graph of the velocity and the horizontal axis, and between 0 and 2. The region is a rectangle. The area of this rectangle is base. It is 2 times height. The height is 10. So after 2 hours, field's position is 20 miles from the origin. Similarly, in this equation, set t to 2. Then after 2 hours, Sasha's position is this integral. This integral is the net area of the region between the graph of velocity and horizontal axis and between 0 and 2. This region is a triangle plus a rectangle. The area of this region is 22.5. So after 2 hours, Sasha's position is 22.5 miles from the origin. Conclusion: if the riders ride for 2 hours, Sasha rides farther. Part C. Which rider arrives first at the 20-mile marker of the race? Interpret your answer geometrically using the graphs of Part A. In Part C, we need to determine when the riders arrive at the 20-mile marker. From Part B, the position of field at time t is given by this integral. Set the position to 20, then I have this equation. This integral is the net area of the region between the graph of velocity and horizontal axis and between 0 and t. The region is a rectangle. Area is base times height. It is 10 times t. Solve this equation for t, then I get t is 2. So field takes 2 hours to arrive at the 20-mile marker. Similarly, set the position of Sasha to 20. Then I have this equation. This integral is the net area of the region between the graph of velocity and the horizontal axis and between 0 and t. This region is a triangle plus a rectangle. The area is this. Solve this equation for t, then I get t is 1.83. So Sasha takes 1.83 hours to arrive at the 20-mile marker. Conclusion is Sasha arrives first at the 20-mile marker of the race. Part D. Suppose Sasha gives field a head start of 2 miles, and the riders ride for 20 miles. Who wins the race? In the displacement formula, I replace the dummy variable t by tau. Then set A to 0 and B to t, and move this number to the right side. Then I have this equation and also have this equation. These two equations are for the positions of the two riders. In part D, when time is 0, Phil's position is 2 miles from the origin, and Sasha's position is 0. So this number is 2, and this number is 0. Now I set Phil's position to 20. Then I have this equation. This integral is the net area of this rectangular region. It is 10 times t. Solve this equation for t, I get t is 1.8. So Phil takes 1.8 hours to arrive at the 20-mile marker. Similarly, set Sasha's position to 20. Then I have this equation. This integral is the net area of this region. It is this number. Now solve this equation for t. I get t is 1.83. Sasha takes 1.83 hours to arrive at the 20-mile marker. The conclusion is, in part D, Phil wins the race this time. Now, the second topic. In this topic, I present one example about other applications of integration. Example, a reservoir is filled with a single inflow pipe. Let Q, measured in cubic meters, be the amount of water in the reservoir at time t. T is measured in hours. The flow rate of water into the reservoir is given by this piecewise defined function. Part A, how much water flows into the reservoir in the first 25 hours? Q of t is the amount of water in the reservoir at time t. Q of 0 is then the amount of water in the reservoir at time 0. Q of 0 may or may not be 0. Namely, in the beginning, the reservoir may or may not contain water. On the other hand, Q of 25 is the amount of water in the reservoir at time is 25. Then the difference of these two quantities is the amount of water flowing into the reservoir in the first 25 hours. In part A, we need to determine this difference. One antiderivative of this function is Q of t, because take derivative on Q of t, then we have this function. So, by the fundamental theorem of calculus, this integral is equal to this difference. On the other hand, when time t is between 0 and 25, derivative of Q is 800. So we have this equation. Now to find this integral, find one antiderivative of 800. It is 800 times t. Plug in the upper limit, plug in the lower limit, and make a difference. Then we get this integral is 20,000. That is, this difference is 20,000. Therefore, the conclusion to part A is 20,000 cubic meter of water flows into the reservoir in the first 25 hours. Part B, how much water flows into the reservoir in the first 50 hours? In part B, we need to compute this difference. Q of 50 is the amount of water in the reservoir when time is 50. Q of 0 is the amount of water in the reservoir when time is 0. The difference is the amount of water flows into the reservoir in the first 50 hours. By the fundamental theorem of calculus, this difference is equal to this integral. To compute this integral, I split it according to the definition of this function into a sum of 3 integrals. The integral from 0 to 30 plus the integral from 30 to 40 plus the integral from 40 to 50. Now, when t is between 0 and 30, by the definition of derivative of Q, it is 800. So I have this integral. When t is between 30 and 40, by the definition here, derivative of Q is 2600 minus 60t. So I have this integral. When t is between 40 and 50, derivative of Q is 200. So I have this integral. To find the integrals here, I use fundamental theorem of calculus. 800 antiderivative is 800 times t. And 2600 minus 60t is this function. Antiderivative of 200 is 200 times t. Now, plug in upper limit, lower limit in t, upper limit, lower limit in t, upper limit, lower limit in t. Then I have this equation. By a calculator, this number is 31,000. The unit is cubic meters. Therefore, the answer to part B is 31,000 cubic meters of water flows into the reservoir in the first 50 hours.